Alright, ladies and gentlemen, this class recording has started. So, yesterday, we started in on section 5.2. Section 5.2, like it says up here, applying Newton's laws. Taking the concepts that we introduced in section 5.1. Newton's first law, inertia, Newton's second law, acceleration, F equals ma, and Newton's third law, action and reaction, and applying them to given situations. Okay? So, the gist, I'm reviewing what we did. I'm reviewing what we did yesterday. Yeah, this is the one I gave them yesterday. So I'm just reviewing this quickly. It's back on. It's back on the blue tray if you want to grab it. So the big gist of yesterday was drawing free body diagrams. So the title says free body diagrams are useful in applying Newton's laws. What is a free body diagram you were introduced to yesterday? You don't necessarily have to give me like a book definition, but it's what? It's a sketch showing all the forces. Okay? So a sketch showing all the forces, because if we're going to look at the combined effect of all of those forces, we have to know what those forces are. So basically it's a way for us to figure out the net force. And yesterday we took our first step into forces in 2 dimensions, where we're finding the net force, but they weren't along the same line, so we had to find the vector sum, or the resultant vector, and sometimes that involved doing some Pythagorean theorem, sometimes that involved components, and we'll continue to do that during this section here. Okay. Apparently, I was informed this morning that I made a math error in the video. Was anybody watching all the way? It was kind of like right at the very end. So. Oh. Okay. Yeah. Apparently. Yeah. So, but anyway, you get the gist. So hopefully, yeah. Yeah, Brett, go ahead. Well, any picture that shows the forces that are acting on an object would be a free body diagram. They become a little bit more important or a little bit more helpful when we're dealing with multiple forces, and especially multiple forces that aren't like in the same line. If F1 and F2, like if F1 pointed to the right and F2 pointed to the left, we know that we just have to subtract them. But in this case, when they're not like in the same dimension or in the same line, we still have to find the resultant or the vector or the net force, but we can't just add them together. You know what I'm saying? Right? Yep. Yep. And we had like a third guy maybe going this way, right? Yeah, then we just do the same thing, but now we're finding the resultant of 3 forces instead of just 2 forces. Which I think actually one of your homework problems actually went through that, right? So it's the same idea, right? You know, find the resultant vector just like we did in chapter 4, right? Break everything up into components, add the x's, add the y's, and find the resultant then. Because, so here, let's do this. We'll do this, okay? Let's copy this. So if this is our free body diagram, let's say we added a third force, right? In the video, right, we did this. This is F1, and then we moved F2 to go like this, right? And then we found the resultant just like that, right? But if this was F1, this is F2, and then let's say we have a third force like this, which is F3, right? According to the procedure, right? Oh, they're all connected. Goodness gracious. Like, we'd move blue there, right? And then we move orange there, and then the resultant, then the resultant would be this one. You know what I'm saying? Okay. We could do it 3-dimensionally too. We're going to stop at 2 dimensions, right? But orange, because it's not on the x-axis or the y-axis, right? We would break it up into components, just like this, right? And then we'd add red with this one here, because they're both x, then we'd subtract this component in blue because one goes up and one goes down, and then that would give us the components of that purple triangle where purple is the hypotenuse. Okay? Same thing we did with displacements and velocities back in chapter 4. Now we're just doing it with forces. Okay? All right, good. You could do it. One of the things that I kind of mentioned in the video, once you've broken all those up, you can look at x and y separately from each other, just like we did in projectile motion. You can do it with z as well. So if you have a third axis, you can do the same thing. Okay. Go there.
So force equals mass times acceleration. But then if there's no gravity, a lot of people
Sure. Yes, but because we don't have to deal with friction, because friction is a force, and we'll see how that affects things like later on in this chapter. That's why things are quote unquote easier to move when you're in like 0G or in space or whatever it is. Okay? Not necessarily because they're lighter or heavier or different gravity, but because there's no friction, and that's an opposing force that we don't have to deal with. Yeah, think about this. Like, so if you have a boat, like, or let's think about a boat, right? If you had a boat that was like, let's say it's, whatever, a pontoon boat, a 12-person pontoon boat. If it's on land, you can't really push it by yourself. But if it's in the water, you can maneuver it. I mean, not a lot, but you can, right? Because the friction in the water is less than the friction on land, right? So that, like I said, we didn't change anything about the pontoon boat. It's the other forces that we have to deal with are reduced, and that's why it's not necessary. Remember we talked about on, I think, it might have been Friday, but whatever. Forces determine if something moves, but mass is responsible for how much it accelerates. Does that make sense?
Yeah. So if you have the same mass and same force.
Yep.
So friction changes the acceleration.
Yeah, because friction will change the net force, right? Remember, it's not force equals mass times acceleration, it's net force equals mass times acceleration. So if you throw friction in there, that generally makes the net force less because friction is usually negative. Right. All right, good there? Okay, so let's get started here on section 5.2. Now that we know what free body diagrams are, oh, sorry, one last word on free body diagrams. I think I mentioned it in the video, but I'll mention it again. So very rarely am I going to, I would say this, I'm never going to grade you on your free body diagram. A free body diagram is a tool that we use to figure out what's going on. There are some ways that generally you'll see them drawn a little more frequently than others, but if yours doesn't exactly match mine the way I have it written on the board, or if yours doesn't match like the way it shows up in the book, whatever, right? If it helps you figure out the problem, that's perfectly fine. There's ways I'm going to draw them in class that are consistent generally with how the book draws them, but if that doesn't work for you, if you see it differently, fine. Whatever helps you figure out the problem is totally okay with me. All right, now that we know what free body diagrams are, section 5.2 gets a little bit deeper then into, well, what kind of things go on a free body diagram? There are two forces that show up on many, many different kinds of free body diagrams. And those two forces are normal force and weight. Going back to this example that we've looked at a bunch of times, the red car sitting on the track. First, red car is not accelerating, meaning what has to be true if there is no acceleration? What has to be true about the red car? No net force. It could be moving and not accelerating. Okay? But if there's no acceleration, there's no net force. We talked about that gravity is always affecting things. So there's a downward force acting on this red cart. But there also has to be another force, right? How big does it have to be? As big as, yeah, so in this case, if we're just talking about gravity, right? Gravity pulls down, The other force has to be as big as gravity, right? But which way? Opposite, so that when we add them together, we get 0. Okay? The track that the car is sitting on provides that force in the upward direction. We refer to that kind of force as a normal force. As you can see here in the definition, it says, the normal force acts perpendicular to a surface. So, normal is kind of like an old school way of saying perpendicular, like in math. If we talk about two lines that are normal to each other, that means they're perpendicular to each other. But if we think about all kinds of...
Excuse the interruption, please. Thank you to the students who came down for final notice on photo retakes. Faculty, if you have not had your picture taken, we still have a sizable stack of teachers who do not have a picture. Please come down at the end of 11th period, PAC lobby, and have that photo taken. Thank you.
If we think about all kinds of things, gravity affects stuff all the time, yet there are several situations where things don't just spontaneously fall to the ground because something gets in the way. There is a force that prevents them from falling. That force we refer to generally as a normal force because it is perpendicular to the surface that causes it. This track provides a force straight upward on the cart to balance out gravity. The floor that I'm standing on provides a force upward that balances out the force of gravity so I don't fall down. The chair that you guys are sitting in provides an upwards force that balances out the force of gravity to prevent you from falling to the floor. Okay? These are all examples of normal forces, perpendicular to surfaces, right? A lot of times it has to do with gravity, but it doesn't always have to, right? If I take this container and I push it on the wall like this, okay, there's a force coming out of the wall horizontally that's pushing against the container, the same as I'm pushing into the wall, so there's no acceleration. That's a normal force. It comes from the wall, but it's still a normal force. Okay? Same thing would be true if I took this and pushed it up onto the ceiling. Right? There would be a force from the ceiling that's opposing my push. That's a normal force as well. A lot of times it goes upward, but not always. It's perpendicular to the surface that causes it. Okay? So it's down, but if the ceiling's causing it, Krista, it's still perpendicular to that surface. So yeah, it's, a normal force is always perpendicular to the surface that causes it. Good. It's basically, there's two ways. One, it could be a positive, negative, or so like a negative repulsion from electrons in the surfaces of the two objects. Or if it's something that is somewhat elasticy, that elastic force that's, right? If I take this rubber band and I hang something on it, it stretches, right? Because the rubber band applies a force trying to get back to its normal position, okay? Right, and that's the like spring or something like that. We'll talk a little bit more about that on Thursday too, but there, yeah, it's generally either a negative repulsion or an elastic force of some kind. So. But one force that influences normal force in a lot of situations is gravity. Okay? So, real quick, let's go here. Nope, not there, but here. And, all right, good with this one? Yes? Yeah. We talked a lot about the acceleration caused by gravity back in chapter 3 and then in chapter 4 when we were doing projectile motion. What do we know about the acceleration caused by gravity? Right. It's always negative. Well, how about this? It always points which way? Down. Most of the time we call it negative, but depending on how we set up our frame of reference, right? What else do we know about the acceleration caused by gravity? Here on Earth, that value is 9.81 meters per second squared. That number is so important that we gave it a special representation, right? A special notation. What did we use to represent that acceleration of gravity? G, right? So if we're talking specifically about gravity, acceleration gets replaced with G. Mass is still mass, regardless of whether it's being accelerated or what it's being accelerated by. So, if we talk specifically about the force of gravity, or sorry, the acceleration of gravity, that will give us the force caused by gravity. And we give this a special name. We call this the weight of an object. The weight of an object is the force caused by gravity. If gravity causes an acceleration, which we know it does, back from chapter 3 and chapter 4, there has to be a force, because in chapter 5 we started answering that why question, right? Before we didn't care why, we just knew it was accelerating. Now we have to figure out the force. So, right, weight is the force exerted by gravity. The weight of an object is equal to m times g, where g is the acceleration of gravity. Okay? Good there? All right, let's take a look here at this one, down at the bottom of your first page. Okay? So it says diagram. So it says a 9.3 kilogram child sits in a 3.7 kilogram chair. Her feet do not touch the ground. So part A says, draw a free body diagram for the child. So yesterday we learned free body diagrams are what? A sketch of all the forces. It starts with a picture. Your picture can be as detailed or not as detailed as you want it to be. There's a kid sitting in a chair. Feet don't touch the ground. Doesn't matter. All I want in this free body diagram is a picture of the kid and the forces that are acting on the kid. Okay? So, a lot of times, we will draw a dot on our free body diagram that represents the center of the object, which also, in a lot of cases, will be the origin of the coordinate system that we use for our problem. Not always, but a lot of times it will be. Okay. All right, so forces acting on a kid who is sitting in a chair whose feet don't touch the ground. First force we can put on this drawing is what? Gravity. Okay? Gravity always acts which way? Down. So we'll start this arrow at the origin pointing in this direction. Okay? We just learned that the name of the force of gravity is what? The force of gravity is called the weight. So we'll label that as W. Okay? And we also just learned that in order to calculate the magnitude of the weight of an object, or the magnitude of the force of gravity acting on an object, we have to do what? Mass times what? That's better. Mass times the acceleration due to gravity. We know that here on Earth that value is 9.81, right? So let's hold on to the negative just for a second. Okay? All right, so plug that into your calculator real quick and find out what the force of gravity or the weight of this child is. .2 newtons. Does that work? All right. So somebody asked this morning, that weight is going to be a Newton's value because it's a force. Okay? It's not the same unit that we use to measure weight here in America, right? Because America, right? Yeah. Veterans Day, right? We fought for our freedom to use different units from everybody else. Okay? But I would imagine so, but literally every other country. So. Hey, freedom. Okay. So. Blue. Yeah. Okay. if this child is sitting in, so this is weight is always a force. It's the force that gravity is acting on an object. Okay? If gravity was the only force acting on the object, what would happen to this kid? They would fall, but that's not happening, right? Meaning there is no acceleration. If there's no acceleration, what has to be true? There's another force. Which way does it act? Upward. How big does it have to be? Exactly the same as gravity. Not bigger than gravity. If it was bigger than the weight, what would start happening? Acceleration upwards, right? Where does that, so we know that this force has to be 91.2 newtons. Where does that force come from? What is that provides the upward force to the child that prevents it from falling downward? The chair. So because that is a surface, we would label that as normal force. Okay? Because it's coming from the surface of the chair. Simran, go ahead. Okay. Yep. Right. So while it was supporting the child, yes. But when it collapses, no. Or it may be providing an upward force, but it isn't. It would be a normal force, but isn't exactly the same as gravity. Does that? It would still be classified as a normal force. That would be okay, but it doesn't necessarily. So normal force doesn't always have to be the same as gravity. A lot of times it is, but not always. For example, so draw a free body diagram for the chair. Okay? So there's my chair. Okay? There's a circle, right, to represent the middle, the origin of my reference point, okay? Or the origin of my coordinate system. There are now 3 forces acting on the chair, okay? Gravity was acting on the kid, but gravity also acts on the chair. Regardless of which object gravity acts on, we still call it what? What do we call the force that gravity exerts on an object? Its weight. And we calculate its weight by multiplying its mass by the magnitude of the acceleration of gravity. Okay? So go ahead, somebody punch that in and find out what the weight of this chair is real quick. 36, we'll go 36.3. How's that weight? Is that okay? Okay, so 36.3. Now, there is another force acting on the chair. The kid is sitting on top of the chair, and gravity is pulling the kid down, and therefore it's applying a force to the chair itself. Does that make sense? Okay? That force is also going to be in this direction because it's on the kid is on top of the chair, the force pulling down, right? Okay? I'm going to call this F sub C for force of the child, okay? And it's being caused by gravity being pulling on the child, so how big is that force going to be? It's going to be 91.2. Does that make sense? Okay? Now, right, if these were the only 2 forces acting on this chair, what would the chair start doing? Falling, right? But it's not. So what's preventing the chair from falling? The floor. The floor is a surface. It's pushing which way on the chair? Up. So that makes it a normal force. But how big does that normal force have to be in order to keep the chair from falling through the floor? It has to be the same, right? But what are we going to have to do with our 2 downwards forces? We have to, these 2 downward forces together have to be balanced out by the 1 upward force, right? So it's 127.5, okay? So this normal force then is 127.5 newtons, okay? Because it has to end up with a total net force equal to 0. In this case, normal force was equal to gravity. In this case, it's not, okay? So usually there will be normal force. Whether it's equal to gravity or not depends on the other things going on in that situation, okay? Yeah, that's what we're going to talk about a little bit more tomorrow, actually. But we have one more problem that we want to do today. So I want to do it. If you guys want to do it now. All right. So let's go here. Let's take a look at the back of page 1. Oop. Make this a little smaller so it all fits on this page. What? Oh, yeah. I mean, it's faster than an elevator, you know what I'm saying?
But like, why not just like jump then? I mean,
well, maybe not kill yourself, but if you break your leg, you can't go, you know. So here, actually, Luke, let's do this. Okay. All right, so it says, fire alarm goes off, and a 97-kilogram firefighter slides down a pole with a constant acceleration of 4.2 meters per second squared. What is the upward force exerted on the pole by the exerted by the pole on the firefighter? So I'm going to label it as a vector because it is. Okay. So in this case here, they've given us pictures that represent the forces. Either one of these I would consider to be a free body diagram because it's a picture showing forces. Just the one on the left is the one on the left is just a more detailed free body diagram than the one on the right. Whatever. Okay. No, it's just a dot, which is fine because if we're just looking at that's the dot representing the firefighter, that's okay. It's showing the forces that are acting on it. So technically it is a free body diagram. Okay. All right. It tells us that the mass of this firefighter is 97 kilograms, slides down with an acceleration of 4.2 meters per second squared. In this picture, they gave us a coordinate system where the floor is the origin and up is the positive y direction. So if the firefighter is sliding down the pole, right, that means his acceleration is going to be what? Negative 4.2 meters per second squared. Okay? Just because it's negative doesn't mean it's slowing down, right? That's just a directional thing. If you start at the top at rest and slide down with a negative acceleration, you're going to speed up. You're just speeding up in the negative direction. Okay? All right. Looking at the picture here, are the forces balanced as they've drawn them in the free body diagram? They can't be balanced. If there is acceleration occurring, right? Acceleration only occurs if there is net force, right? These two forces can't be balanced or there wouldn't be any acceleration. Okay? So, acceleration means we go here, right? Newton's second law. How many forces are acting on this firefighter? 2. Okay? Does that make sense what I just did there? Remember that net force is the sum of the forces, so all I did was sum those two forces that are there. Okay? First, do we know what the weight of this firefighter is? Not right now, but we can figure it out, right? How do we figure out the weight of something?
mass times acceleration given
All right. Anybody got that real quick? We can get it done. Don't worry. We'll get it done. Okay. But which way is that weight? Which way is that weight pointing in our picture? Negative. Okay. When we use this arrow that's pointing in the downward direction, in an equation, we have to make sure that we represent the direction by making that negative. Okay? Plus the force, which we don't know what it is, we're solving for that, equals 97 kilograms times negative 4.2 meters per second squared. Okay? When you do that, you should get a positive number, 500 something. What is it? That sounds right.
544.17.
Okay? So, first, bigger force down than up, meaning acceleration will occur downward. Okay? Simran, to answer your question, or to go back to your question from before, is this F in the picture, this force right here, is that a normal force?
Yes.
No.
No.
Because it doesn't come from a surface. Okay? It's opposite gravity, but it's not necessarily a normal force. This would be more of a frictional force because of the friction between the guy's hands and the pole. Okay? Even though it went upward, right, it doesn't necessarily mean it's a normal force. No, it is perpendicular to the motion of the object, but it's not coming from the floor itself. It has to come from a surface, a floor, a table, a chair, something like that. You wouldn't treat it any differently in a problem, but technically it's not a normal force because it doesn't come from like a surface. Okay? It doesn't change how we use it in a problem. It's still positive in this case, but technically it's not a normal force because it didn't come from a surface. Okay? But like I said, it doesn't change how we do the problem. And the fact that it turned out to be positive is good because in our picture it points in the upward direction, and that's the positive direction.
So, alright, the way I got that answer
Yep.
is I took 9.81 and subtract 4.9
Okay, you could.
Now it's the same.
Why don't you just solve this equation?
I did.
Okay.
I just did it. It's
Right.
the same answer.
It does that the
That's
same
why I was
because
thinking that.
this number, so what you basically did was this, okay? So here, let me do this in a different color. So, this is basically what you did, okay? So, okay? And then does that make sense? Okay. It just so happens in this case A is negative, and so that's why you subtracted them, and that's why you technically you got the same answer because this weight force is dependent upon the mass. So you can do it that way. That's okay. But if we had another force, like an applied force or something like that, you wouldn't be able to do that. Okay? In this case, because we're dealing just with a force that is dependent upon the mass of the object, that works out mathematically. Okay? Yeah. Yep, and it's basically the frictional force of the guy's hands. Yes, and tomorrow we'll get into that a little bit more. But that's sort of like the lead-in to tomorrow, that just because it goes upwards doesn't necessarily mean it's a normal force, but normal force doesn't always have to be equal to gravity.